So let's start with forces in space. Let us consider that this is a force which lies into the three planes. This is a 3D diagram which you can see, where this is the x-axis, y-axis which is perpendicular to x, and this is the z-axis as I am showing the cursor on the screen. The angle which is made with the x-axis and the force is theta x. Again, the one which is made with y-axis and the force is theta y, and respectively the third one is theta z. Now moving on a bit ahead, if we name the edges of each of them, for example, this is the diagram of force system, and this is the force which lies in this 3D diagram, and we can see that we have named it E, D, C, B and A. That these are the corners, and O, these are the corners of this cube, this rectangular 3D diagram representation. From the diagram we can see that if we consider this triangle OED, according to the hypotenuse theorem, we can see that OE square is equal to OD square plus DE square. Further, OD it can also be said that OE square is equal to OA square plus OC square plus DE square, that is this vertical one. And with the same logic, we can get into the conclusion that OE, that is F square, is equal to Fx square, that is the x-axis component of this force. The y-axis component is Fy and z-axis component is Fz. And they are split. Going to the previous diagram again, they are split here in terms of theta as F cos theta, F cos theta x, F cos theta y and F cos theta z. We had obtained an expression in the previous part of the video where we had claimed that OE is equal to Fx square plus Fz square plus Fy square, which we have all together put in one frame so that you can understand the expression better. So this is the ultimate magnitude of the force we can get. If this is a vector force F, the magnitude of that force is given by under root of Fx square plus Fy square plus Fz square. Fx, Fy, Fz I've discussed before and also mentioned here in the PPT, in the video, that is F cos theta x, F cos theta y and F cos theta z for Fx, Fy and Fz respectively. So based on this, we can also obtain the value of cos theta x, cos theta y and theta z, and the angles of the force with respect to each of the axes can be determined. As of now, we were discussing in terms of theta, that is the angle between the axis and the force. Now let us discuss about if this is a point and has to be explained in terms of coordinates. For example, consider the point A will have coordinate dx, dy and dz with respect to the x-axis, y-axis and z-axis. For example, this is the point A here. It lies at a distance dz, so this dz component lies. It lies from a distance dx from the origin and hence dx is considered. It is at a height of dy, so hence we have considered the component dy. So this is how we mark the coordinates of any of the point in a force system. Moving on ahead, to understand the concept of unit vector, I have given some basic explanation. What is unit vector? It is vector which is having a unit length. In mathematical expression form, we can say that unit vector is equal to force vector divided by the magnitude of the force vector. So force vector F bar can be represented which is equal to lambda into F. This lambda here represents the unit factor of our discussion. So unit vectors along the x, y and z axis will be I, j and k. So if we are talking about vector F, it will be Fx into I, Fy into j and Fz into k. This basic might be discussed in one of your discussions where space forces was discussed in your curriculum. Now see, if a vector force F is defined by the coordinates of 2 points A which is having x1, y1, z1 coordinates and B which is having x2, y2 and z2 coordinates. We will measure the coordinates as I had explained in the previous diagram. presume that this is a point A. What if the point A lies here and point B lies here on the force on this complete force, and the force is passing through this point A I am plotting here right now, and point B here. I just have marked two of the points randomly, or you can assume that there is a point A here and point B here. So in that case, the coordinates will be x1, y1, z1 and x2, y2, z2 respectively for A and B. So if we have to calculate unit vector for that particular force which is passing through the coordinates A and B, we get the unit vector and can be represented with the formula x2 minus x1 into I bar. This is the vector component, unit vector component, which is represented with respect to x-axis. Y2 minus y1 multiplied by j bar, which is again the unit vector component for y-axis, and z2 minus z1 into k bar, the same vector unit vector component for z-axis. This is divided by under root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. Now what we'll do, we'll just substitute this x2 minus x1 as difference of x, that is dx, dy and dz, and this whole can be expressed with the total distance d for that unit vector lambda ab. So solving this expression, ultimately we get f bar is equal to, this should be f bar here, what I'm pointing right now, the f bar is equal to f into lambda. So we can express it in terms of f upon d is equal to all of these f and d taken together outside the bracket. So we get dx into I plus dy into j plus dz into k. You will get this explanation better when I proceed with the example, and we actually learn in terms of experimental values. Now what is this? This is the experimental apparatus assembly. The aim of our practical is to study non-coplanar concurrent space forces experimentally and analytically. So we have prepared an experimental setup. We will calculate the value of determined forces experimentally, and we will try to solve them analytically with respect to the theory what I've explained here in this figure. And based on this, we will compare both of them and try to find out the error between the experimental and analytical values. I will just explain you the procedure first, and then I will take a sample calculation for you guys to understand. Now you can see in assembly here, what we have done is we have tried to build up here a non-coplanar concurrent force system. How we have done that? This is a board which is T-shaped at the base. You can see that there is a origin point here where the cursor of my video right now is. The center point from where this blue line towards A and blue line towards B starts, this is the origin point, you can say. And you can see that one flap of the T, one side of the T flap has A written here, the other edge has B written over there. The other end here is written as a C. Here it should be a pulley or a weight which is connected with point D and D dash here. I have not mentioned D dash and D here, so please try and cooperate with the video. So what we have done here exactly is, we have made this assembly of two rigid bars AD, which I can show you. This is AD, the blue color one, and BD, that is the red color bar, you can see here, and these are placed at fixed position. And there is another tie bar CD. This is C and the above point is D, together with a provision for loading at D. Now what we are trying to do is, we have made a provision connecting all these two rigid bars and this one together, this rigid bars AD and BD and the tie bar that is CD, we have connected together at point D, and we have applied a weight W here. Okay, now what we are going to do is, we are going to note the distances from the origin, that we are going to measure the distance OD. We are going to, with the help of a tape, for measuring the distance OA and OB, there is a scale mentioned here on the apparatus. We also measured the distance OB see, I will explain you why we are writing down the distances here when I explain you the observation table ahead. So this is how the assembly is made. We note down the distances for the respective weight, and we note down the tension or the force which can be determined with the spring balances we have attached to each of the bars. That is, you can see this smaller rectangular white color shape. This is spring balance which gives you the value of force in that particular bar when we apply the weight. This is how the assembly apparatus setup is. We take the first reading accordingly, then we change the distances of point A with respect to the origin, also from point B with respect to the origin. Also we vary these distances and again take the values. So I will explain you one set of reading here. The force which we are applying, the first column here is force F in Newton. That is the weight which we are applying will be in kgs. So we are assuming that this force will be in that force that weight what we were applying was in kgs. We have converted into force, multiplying it by 9.81. We have noted down the distance OA, OB, OC, OD and D into D dash. Now we will point the coordinates in meters. Whatever distance we have written here, we will mark down the coordinates here. As I had shown you in the previous part of the video how to mark the coordinates, you will mark the coordinates for point A, B, C and D with respect to x-axis, y-axis and z-axis. Now where is x-axis? X-axis is along this line AB which I have shown. Y-axis what we have considered is here, which is towards the tail of this T, and z-axis is in the direction which is perpendicular to the board. So experimentally we will get the values which we will be seeing in the tension within the members, the tension member TDC, then FDB, the force member, and FDA. So experimental values can be filled here, that is FDA experimental value will be filled, FDB experimental value will be filled, and similarly for FDC the experimental value will be filled. With the help of the spring balances here we can note the values. Let us take one setup of readings. Assume that these are the readings what we have obtained and as the coordinates, and let us consider that the weight or the force which was applying in the downward direction here is 30 newtons. Now as per the formula we will apply it for all the three force members, as we have to determine the analytical value for all the three force members. The formula will be x4 minus x1 into I bar, y4 minus y1 into j bar, z4 minus z1 into k bar, divided by square of each of the brackets and addition of it multiplied by this fdA. This initial part is lambda into dA, that is the unit vector, and this is the force. Now we don't know the value of f into dA, so we'll express this equation f bar into dA in terms of fdA, and we will multiply with the unit vectors of each of the axis. So moving ahead, in this form, this is the formula for FDA, that is our first force member. Now for FDB, similarly the formula will be x4 minus x2, that is the coordinate for the member FDA. The coordinates are D and A. For the second member, that is FDB, the coordinates are FDB, and the third one, that is third member, is TDC. So for the first one the coordinates will be D and A, the force will be passing between D and A. For the second force, that is FDB, the force will be passing between the points D and B, and the third one, that is the TDC force, will be passing from the points D and C. So based on the coordinates we will do value substitution, and after doing value substitution we will get the equations in this form in terms of unit vectors of I, J and K, and we will similarly get the three equations for each of the force members, that is FDA, FTB and TDC. Now what we have to do, we have to apply the equilibrium conditions, and applying the equilibrium conditions of Fx is equal to 0, Fy is equal to 0 and Fz is equal to 0. This is the format in which we will get the values. What we have done, is for fx addition of all three in terms of I, for fy addition of all these three, and for fz addition of all these last members of k unit vector. Since I is the unit vector representing the x-axis, j is the unit vector representing y-axis, and k is the unit vector representing the z-axis, we will get the equilibrium condition of f is equal to 0, fy is equal to 0, and fz is equal to 0. So you can see here that I have applied, and I have also multiplied these factors fda, fdb, tdc, that is the force members which we don't know. So solving all these three equations, you can get the value of FDB, FDA, and TDC. Now, for summation of Fx, it is only the addition of the unit vectors in x direction. For Fy, all the addition of unit vectors in y direction. But for Fz, we have addition of unit vectors in the z direction, and the weight component, that is minus w, is to be considered here in this equation. So solving this equation, we get the values of each of the forces. FDA is equal to 37.46. Similarly, we got the value of FDB and TDC. And here this value of W was substituted as 30 newtons, as we had considered in the previous part of the example. So this is how you will fill the table number T1, solving the analytical values for force FDA, FTB, and TDC. For this is your first set of readings. Now you will shift the values of places of A, B, and C, and you will again take 5 such readings. So your whole table will be consisting of 6 set of readings. So this is the first set of sample calculation what I have explained. You can try it 5 more times, and there will be a table like this. So what you have to do in this table, that is table T2, you have to initially take the difference of experimental and analytical value, which you will be filling here, and you have to note down the percentage error. So percentage error can be calculated with analytical minus experimental divided by analytical, modulus of it into 100. So this is how we can evaluate and perform the non-coplanar concurrent force system experimentally, and we can verify the values analytically. Thank you.